Hello world! In our last gripping installment of trying to program some Windows screensavers on my Agon Light, we managed to replicate the Mystify and Starfield screensavers. This week we're going to go completely off the rails in our attempts at creating the marquee and flying Windows ones, but we'll end up accidentally creating something approaching a kind of demo type thing instead. First, let's watch some screensavers for a minute and see what they do. Here's the marquee screensaver. It just draws scrolling text on the screen. How it did this was actually pretty clever. You see, early versions of Windows had no APIs for drawing game-like effects. Text lived in labels, and they were attached to windows. So I think all this is doing is drawing a large black window and then dragging a label with your words in across the screen. The Flying Windows screensaver is a little bit more elaborate. It's the Starfield from last week, but with Windows logos zooming out the screen. Except they're not pictures of Windows logos. This is part of the Wingdings font. You know, that funny one with all those weird symbols in, that kind of has now been rolled into emojis and everything. There is a Windows logo in it. And I think all they're doing is drawing labels of different sized text and moving them so they look like they're zooming out the screen. So it's all just a bit of a trick, this stuff. Which is pretty good, because what I'm going for today is lots of little tricks, as you'll discover. Now before we get too distracted with the Windows screensavers, let's not lose sight of the point of this. I'm trying to learn how the Agon works and how to make games for it. I'm not really trying to clone the Windows screensavers, so if I don't end up making them, I don't really care, so long as I've learnt something new. Which gives me a nice excuse for when I can't actually make some of the visual effects that we're trying for today actually work, as you'll discover. This week's mission is to figure out how graphics work. It's fine being able to tell the VDP we want to draw lines and points, which is what I did last week. So if you're not quite sure what's going on, somewhere around here will be a link to last week's video. Go have a look at that as well. This week though, what about bitmaps? How do we get pictures on the screen? How do we get them in the device in the first place? Because if you've done any embedded programming, this is the bit where we have to probably mess around with image converters that turn bitmaps into C header files and then include all that mess in our code, and it's all very rigid and like compiled into the binary. Well, fortunately, we're going nowhere near that crap, because the Agon has an SD card. Its C libraries can access files off the SD card. We can store images as files on the SD card and load them at runtime into all this RAM that we've got, just like a real computer. I don't think it can load PNGs though. The first thing we should probably do is look in the documentation to see what we can even do relating to graphics and bitmaps. So let's just nip onto my screen and have a look at the documentation. So the Agon and Console 8 comes with this really nice documentation system that lists quite a lot of stuff. Now the things that I'm talking about today, you need the latest version of the Console 8's VDP, kind of says here. This is all based off something that was created by Acorn back in the day, and it's been expanded. So some of the documentation is from the old system, and then it's been blended with the new version that they've done now. And it's trying to explain here what a bitmap is. Now, a bitmap to the Agon is just some sort of buffer that it understands as being some kind of image, and then we can put that on the screen. If we look down the side, there's lots of different commands that we can play with. There's this concept of selecting a bitmap, and then this idea of loading bitmap data into the current bitmap. And then later on, there's things like drawing the current bitmap on the screen. So it's kind of like some of the other graphics libraries you might have used, where you've got to choose the thing you want to use first, then everything else relates to that thing you've chosen. So if I want to load data into a bitmap, I first have to select which bitmap I'm talking about. Now they're just an 8-bit number, but actually they're not. They're actually 16-bit numbers. There's a little bit where it tries to explain this. And you'll see some of these things. It says here, select a bitmap using a 16-bit buffer ID. We'll use this command later on. We might use this command too. I'm going to go through the C code later to understand how this works, and I'll show you an example that I've been using. But the general idea is that we can stuff data inside the ESP32. and then just use code to tell the ESP to draw it on the screen for us. Something that's a little bit awkward is that there is a command here that loads bitmap data into the current bitmap. So if I could somehow get my PNG turned into whatever bitmap data this thing needs, I can use this VDU command to load all the bytes in. But if you think about that for a minute, my bitmap might be like 32 kilobytes of data. So I'd have to construct this massive long, literal 32 kilobyte long VDU command and run it, which would stall the machine whilst that was being uploaded. So there is a better way to do this, which is hinted at up here, where it says Buffered Commands API. So the Buffered Commands API is a massive rabbit hole, and I'm not going into it because I don't really understand much of this stuff. It's one of these things that I can use it, but I don't quite understand internally what's going on, which kind of annoys me because I like to know what things are doing. But this works quite well for bitmaps. It also lets you load sound samples in, and you can load VDP commands in there as well. So this is a way of just getting data into the ESP, and then you can tell the ESP to use bits of it later on. They switch between blocks and bitmaps quite a bit. A block is something that you load data into, and then you have to turn it into a type of data once you want to use it. So if I load lots of pieces of images, like maybe I take my PNG, convert it into some sort of whatever format this thing needs, and I send line by line from the image into the VDP, they'll just appear as multiple blocks. To draw it on the screen or use it as a picture, I need to convert it into a bitmap, which means I need to combine it. There is a command that does it for you, you don't have to think too hard. And then if I want to draw a bitmap on the screen, I can just select the bitmap using its ID. I then convert it into a bitmap by saying its width and height and format, which we'll look at down here. And then there's just a VDP command for drawing the selected bitmap to the screen. So once we've got the data in the Agon, it's quite quick at loading and showing pictures on the screen. So far I've just been talking about bitmaps as like this sort of vague thing. So now we need to understand what a bitmap is. On the Agon, it's one of these things. It could be a 1-bit per pixel image. It could be a, is that 32-bit pixel per image? Or it could be this one, which is an RGBA 2222 format. Now these different image formats, if I bring up some sort of color picker. So here's a color picker in a paint program, and you can see there's like literal millions of colors to pick here. And they're all represented by a large hex number. This is the same 88888 or whatever it was format that the Agon understands. You can load in actual photographs into the Agon. However, it's only got a 64 color pixel screen. So it can literally only show 64 colors, and the 64 colors are fixed. It's not like a big palette. So it's better to load your images in as RGBA 2222 format, where you have 2 bits per channel, and it's ordered alpha, blue, green, red, just to be really confusing, not that way around. When I was making an image converter, I got it the wrong way around and all my colors were backwards. So we've just seen that we need to somehow load bitmaps into the machine, but we store them on our computer as PNG images. Somehow they need turning into some sort of what they call an RGBA 2222 format image. What this means is for every single pixel in the image, it needs to be turned into a representation that for the red, the green, the blue, and the alpha parts, you're only using 2 bits. Which, if you can count, means that each pixel is going to use 8 bits. So this is an 8-bit per pixel display. And there's only 64 colors. So we need some sort of conversion to do this for us. This is where often graphics gets a little bit confusing. However, because I'm a bit lazy, but also I didn't want to get distracted and stuck and lost trying to figure all this mess out, I just hopped on ChatGPT and had a little chat with it. So let's have a look at what it came up with. So it actually turns out that I've lost the original chat that I had with ChatGPT where we sort of reasoned this out. But the end result is this Python code that I've got, which is included in all my code that I release anyway. So we're using the pill, or I guess it's pillow image stuff for Python. And I've got a function that converts the image data to 2222. and you give it a source image. So first we need to load the file. So here's a file version. So we open the image. We first convert it to RGBA, because if it's not got the alpha channel, none of this works. We then have to quantize the image down to 64 colors. I don't know what this really does, but this works. So if you understand what that's doing, I know it's doing a lambda function on every single pixel in the image, but somehow integer dividing the pixel by 85 times 85 chops all the colors down to 64 colors, but does it properly. We then pass it into this thing that converts it into the correct format, which is up here. So we take the width and the height and the pixel depth. We then get all the pixels and we create a byte array, because Python's understanding of lists and arrays is bonkers, so we have to tell it a specific array of bytes. Then for each pixel, we unpack the RGBA part, and we do this quite simple binary logic to it, which just makes sure we shunt the correct parts of the red, green and blue into the correct parts of what the pixels should be. And then we put that into a file. I'm also writing this little header, which I attach to all my images so that I can internally check that it's a bitmap. I can read in the width and height. I then know like what else it is as well. And then the data goes in. So this is my own image format that I'm using, which goes to show that the Agon doesn't care what format you're providing the data in, so long as the actual pixels are in RGB 2222 format. Now what I've done is turned that code into an actual little tool, which all you need to do is run, and then you feed it an image and a folder to put the image in, and it just converts it for you and puts .222 at the end so you know it's not the PNG. And I use this inside the makefile. So I just use this horrific bit of makefile magic to go through the images folder in the source directory, and it converts every single image into a 222 format file. It does the same for some other stuff that we'll look at in future videos, so at tile maps and fonts. In fact, fonts comes later. Fonts are just pictures, same thing. So now I've vaguely sort of explained what the Agon does with bitmaps and how to get bitmaps into the machine. Let's actually look at some examples. So let's crack on. Enough waffle about the documentation and my code that I've written that converts images. Let's see something else. I've got my logo. I've got another logo that you might recognize, and I think we can make them move across the screen. We can't do zooming because there's no routines yet for scaling bitmaps, but that's fine because I'm not trying to replicate the Windows screensaver like I said. I'm now off doing my own creative coding. This is the whole point of doing this. I had a starting point, I've tried to get to it, discovered there's something I can't achieve, but that doesn't matter because I'm learning things as I go along. This is why I picked Windows screensavers. At some point, I just can't get any further. But now I'm off on a tangent, and that means I'm about to either learn something new or actually apply things I've just discovered to a new situation and properly understand them. So let's see how all this idea fits into my code. Knowing how to put things in the VDP is one thing. Making use of it is another. It's fine that I know how to get the data in, but I now need to think about what I'm actually doing. So the first thing I need is a way to store positions, which is what I've got here. So I've got this sprite structure, which stores a position and the bitmap ID. I've then got an array of these. I've got 10 of them. I've also got a font, which is another thing that's very similar to a bitmap image. So the first thing I'm doing is changing screen modes into mode 136, which is a buffered 64 color mode. I'm then loading in my logo, and it loads it in as a buffered bitmap image. This load bitmap into buffer command we'll come to in a minute. I'm using it quite a lot. I'm then assigning it to a bitmap, so bitmap number 1. And then I'm loading in this other image and assigning that to bitmap number 2. And then I'm just filling in the array with random positions just slightly off the edge of the screen. I'm then loading a font, and we'll definitely come to fonts in a minute. Then there's just some very basic screen update code, where all I'm doing is moving the X position of the image across the screen. And when it goes off the screen, I randomly put it back at the start in a different position. And it just keeps going around and around and around. So let's see what that piece of code is doing. So here's a command to load a bitmap into a buffer. You need to give it a buffer ID, and then a file name, and a structure to store the header in. And the first thing it does is opens the file. It's literally using fopen. It then reads the header, and it's looking for this magic string so that I know I'm loading an image. It then reads in the header, which contains the width and the height and a few other bits and pieces. Once it's done that, it goes into this loop, and it reads each line of pixels out the image, just using the normal read command, and then it does this add stream to buffer. So let's go and find that. So as you can see, add stream to buffer looks like it barely does anything. It's using VDU command 23A0. We're then writing the buffer ID. We're then writing the buffer size. And then we're just using the print command to print characters of that many out the serial port. This is just sending it across the little serial link into the ESP. And we've told it which buffer to put it in and how big that buffer needs to be. The VDP goes off and does all that magic by itself. We don't need to worry what's happening. The nice bit that I don't make use of at the moment is this is a loop, and it just carries on one after the other. I can do things after it's loaded a line of pixels, and each line of pixels is not very big. So at some point I'll need to implement some kind of loading bar so that you can see that the machine hasn't crashed. Currently when it loads images, the screen is black and you don't actually know what's going on. You just have to be a bit patient whilst it loads. So that loads a bitmap into the machine. To draw them on the screen, we're just using plot bitmap. And here's plot bitmap. All it takes is a buffer ID and the position on the screen where you want to put the bitmap. And it's using VDU 23, 27, hex 20 to select the buffer ID, then 25, ED, and then the X and Y position. And it just puts it on the screen. This is the plot command, just with a different mode. And again, this is really short and simple. I'm not sending bitmap image data to the VDP or drawing it on the screen by hand. This follows the same idea of last week where you give it commands and it does it for you. To draw things that scroll across the screen, they need to start off the screen, which can get a little bit tricky because on most computers you can't draw off the edge of the screen. It doesn't exist. You're usually drawing directly into RAM, and you've got a specific memory location that is video RAM. And if you try and draw off the right or left edges, you end up just being on the other side of the screen because that's just a giant long array. Until you reach the top or the bottom, and then you're just drawing outside the screen memory in other bits of RAM that you're not supposed to, which is fundamentally bad. At best, you're drawing in RAM that you've not used yet. At worst, you might draw over your code and crash the machine. We visualize the screen as being a giant rectangle, but to the computer it's just a massive long array. Except the BBC and the Agon is different. If you look on the screen, you can see this little diagram of the screen coordinates, and you'll notice that there's 0, 0 in the middle, and then it's got a box that says typical screen. This is what we see as being the image. But there's negative coordinates going both ways. This is called operating system coordinates, and they're really frigging confusing when you first start using it. In fact, there's some of you out there that'll be like, I turn that crap off the second I use the machine, and I just use the screen pixels. Why are you doing this? It's bonkers. Well, the reason is, for this screen mode, I can use the negative pixels to draw off the edge of the screen. So I can draw the little R in my N logo off the edge of the screen, and then just increment them as they move across, and when they go off the edge of the screen, nothing bad happens. If I'm trying to do this using the other screen coordinates, I don't know where I'd put them. And I'd have to maybe do something weird where I'm drawing individual pixels as they go off. But this is how the screen really is. With the weird thing where 0, 0 is the bottom corner, not the top. Just to really confuse you. But you get used to it after a bit. So this code is quite, it's very, very simple when you get down to what's going on. There's no really crazy bit masking or anything that you might see on other machines. I'm just sending very simple commands. But it results in this effect that you're now looking at, which looks quite cool really. There's little logos sliding across the screen, and there's some scrolling text. So let's look at the scrolling text because that's wiggling about in a little sine wave pattern as well. So let's go back on the machine and have a look at the code for that part. Because I've gone into there's some fonts and we'll do fonts later. So now it's later. Let's look at the fonts. So we're back in the code again, in the beginning of the screen. So what we do is, oh, by the way, this screen init stuff is stuff I've made up myself. I've created this whole sort of state machine of being able to switch screens. This is not built into the Agon. You can literally do what you like. So after loading the images in and making however many of them, I'm calling this load font function. Now what this is doing is loading my own built-up font format that I've invented. If I just go into the files that I've got and find the images that I'm working with. So there's my logo, there's another logo, here's a font. This is how text used to be done before computers had like TrueType fonts and everything. You'd draw each individual character as just like a little square of pixels and then stick them all together in, hopefully, ASCII order, so that you can very easily just use some very simple maths to work out which one of these you're working with. Now, because you can't cut these out of an image on the Agon, I've got a Python script that just cuts this up into separate pictures, converts them into 2222 format, and then makes a big list of each one and what the file name is called. That's what I use when I'm doing this load font. That's what this font thing is. It's just like a definition file. And if we go in here and we can find it. So here's load font. It first loads the font definition. So if we go down here. Nope, lost in my own code. Here we go. So it goes to this load font def thing, which first opens the file. It reads the heading to make sure it's a font and nothing else. It then reads in the header, and the header tells me various pieces of information. It tells me the name of the font. It tells me how many characters it's got. It tells me the width and the height and what starting bitmap ID in the VDP the first character is going to be assigned to. There's then various other bits of code that loads it in and loads it into a buffer, just as if it was an image, and then assigns a buffer to the bitmap for each individual character. If I want to print them on the screen, I then just use the same printing stuff that I've used before. So here's a put character function that takes the font, takes the coordinates, and it takes the character to put on the screen. This bit works out whether I'm trying to print a character I don't have a font image for. And if I do, it just prints character number 10, which I think is just a star. And it draws it on the screen using port bitmap. I can then use put string, which just uses this, but multiple times. And I can use printf, which uses put string, and works out what to print as well, and converts things. The wibbly bit that does the sine wave is here. So I've got my scrolling text, which is just whatever. I've then got a point, and I'm trying to make that effect where the text moves across the screen, but also wiggles up and down. But not the whole thing, just like each individual character. And that's what this is doing. It's just printing each character with a little bit of basic maths. And again, we're using sine and cosine on a machine that's got no floating point, but we don't care. We'll fix that in another week. We'll keep putting that off until eventually I get it done. And then we just print it. And then we wait for a v-blank and we flip the buffer. And that's it. So the end result, as I kind of showed you earlier, but let's show it again because I'm quite proud of this thing, is this nice little entertaining sort of demo-y sort of thing. I know it looks nothing like the Windows screensaver that we set out to reproduce, but I've learnt loads by doing this. I now know how to do some fairly fundamental things. I can convert a PNG into the RGB format that the Agon needs. I can load that data into the Agon as a bitmap. I can draw it on the screen and move it around. I also know how to cut up bits of text, like the bitmap description of the characters, into small pieces, and then print the relevant parts of those on the screen to simulate lines of text. I've written my own printf, and I know how to wiggle things up and down in a sine wave because, you know, that looks kind of cool. Now the nice bit is, this code, apart from the VDP stuff, is not unique to the Agon, it's just bog standard C code. So if I go for a different machine, like maybe there's something else that I pick up in the future, I can port this code to it really easily. I'll just need to know how to draw on the screen. And now I also more completely understand how the Agon screen works. Like the coordinate system now makes sense to me. I've kind of done it enough that I can cope with it being upside down. And I've also realised that you can use quite inefficient code and it still works fairly well. But I will need to fix that one day, because that's annoying me a little bit. I want to give this code out for others to look at and use, but I'm now reaching a problem where the code is getting quite tightly twisted amongst the programs that use it. It's quite hard to pull bits out that maybe I've used in this video without also pulling out half of the code that I've also written. It's a classic case of I need to write a library. In C this would be easy, there's tools to do it, but the hacked about C compiler I'm using on the Agon doesn't seem to have some of the extra utilities that I need. So I might have to go and ask some people how to do this. But that's definitely a future video. I think I've done enough for today. In a future video, I want to look at more game-like features. Now that I can draw bitmaps on the screen, I need to create actual sprites with collisions. A tile map would be nice, so that I can have a background, like platforms or just whatever. I've got no idea what game I'm trying to make still, so creating all the infrastructure is helpful and it's not at all a delay tactic at all. No, definitely not. Although I have a different idea about making games. I know I originally said I was setting out to make a game for Aegon, and I still do want to. But part of the reason for this procrastination on actually starting is I don't really know what I'm doing, and I can't write a game without first writing all the infrastructure. It's that chicken and egg thing. I could hack some code together and show you like a fake Mario thing, but then I could never turn it into a working game because I'd have to rewrite it all. So I'm going to keep doing more exploratory creative coding on my Agon because it's a really nice platform for working all this stuff out, and I like getting lost in the weeds of what's going on. It's really fun. But I'm going to separately learn how to make games as a separate thing, and I'm going to use modern tools on a modern machine. But that's a project for the future, and I may do that somewhere else. So stick around to find out when I do that, because that'll be a whole separate thing. It'll be quite fun. I think next time, I'll go for something more difficult. I want to make a scrolling tile map engine of some sort, because that'll be a test of the Aegon's hardware and my programming skills. I really don't know how to do that, so stick around, because figuring it out will probably send me off down some other random rabbit hole. So I'll see you later. So back in the code. Oh, for God's sake, the fan's come on. Hang on.